I start recording. Thanks. And okay, so let's begin this discussion session on solving the Ising model in 2+ϵ dimension. And that follows also the discussion that we have had last week with the seminar of Andrea Capelli. So please, you are all our attention. You have all our attention.
Okay, so I can start.
Yes.
So last Friday, in the Slack, in some discussion, I mentioned that I try to deform the Ising model in 2 dimension to 2+ϵ dimension. But then naively, some naive deformation does not work. And then Slav asked me whether this is some published result. And I said no, because it's a negative result. And then he asked if I want to discuss in some formal session. So I think this is a good idea. So that's why I'm here. So I will talk about Ising model in 2+ϵ dimensions. And I try to talk about some analytic approach to study this problem. And I'm a postdoc at OIST, and I will soon join San Diego University as a junior member. So last Friday, there's a very nice talk by Capelli, which is about the numerical bootstrap of the Ising model from 2D to 4D using the single correlators. And we can see that in various dimensions in 2.001 and 2.2, d equals to 3, d equals to 3.75, you can always see the very nice kink behavior. But then there's a comment about the state, about spectrum, which rearrange themselves around d equals to 2.2. And this is something expected because the behavior of the spectrum in 2D and 3D are very different. And in the analytic approach, usually people start from the 4 dimensions and then maybe go to a bit lower, for example, 3.99. And typically we have 2 fixed points. One is Gaussian, the other is the weakly coupled Wilson fixed point. And so here I will follow some notation from last week's lecture's note by Alessandro Ficchi. So here I will call this function capital G, which is the conformal invariant part of the 4-point functions. And then it is a non-trivial function of the U and V, which are the cross ratios. In the case of free theory, it's very simple, just have 3 terms corresponding to 3 different kinds of reconstructions. And in the case of 2 dimensions, we also know since the work of Onsager is an exactly software model. And in particular, for the critical case, it corresponds to one of the simplest minimum models. And here I write the exact solution of the correlator of the spin field in terms of U and V. So we can see it also takes a very nice compact formula, which is not too much more difficult than the free case. We still have 3 terms, but just they are in the square root. So it's very tempting to try to deform this 2D exact solution of the strongly coupled system into 2+ϵ dimensions. And because this is strongly coupled theory, the Lagrangian approach is not so useful. But this is very ideal for the case of bootstrap because we don't use Lagrangian, we just use all kinds of consistency conditions. So in this talk, I will try to talk about how some attempts to try to deform this 2D solution to 2+ϵ dimensions using some analytic bootstrap method. So one question when I'm preparing this talk is that it's well known that the 2D Ising model is equivalent to some free fermions, free Majorana fermions. And naively, by going to 2+ϵ dimension, I guess this will become some kind of weakly coupled theory in terms of the fermionic representation. But I don't know whether some expert in the audience know that if this is something have already been studied before, I mean that the fermionic counterpart in 2+ϵ dimensions. I guess there's some sort of point is that the spin field is some kind of non-local with respect to the fermion fields. But so one question is that if you try to go to 2+ϵ dimensions, whether this mapping is still valid. this side should be some kind of weakly coupled, although the other side is strongly coupled. And whether this kind of mapping extend to 3 dimensions or higher dimensions. If no comment, then I will continue.
Yeah, the question, could you write the theory also in terms of the fermions and do the bootstrap with the fermions?
I didn't prepare this part here. I guess so the typical story is we need to do some Jordan-Wegener transformations, and so sorry, I didn't prepare this part. Maybe we can discuss later.
But the fermions are the 3 fermions. We can write them in any D, but the problem is that the problem is going to be how to introduce the spin field, because indeed in terms of fermions, it's non-local. It's defined as some sort of defect for the fermion fields. So if you go to 2+ϵ dimensions, it's well, you will have a single fermion field in 2+ϵ dimensions, but it's no longer going to be like, it's not known how would you define a spin field. So it doesn't look obvious how to do this. So
okay, thanks.
I think now you can go ahead with what you prepared.
So here I will formulate the problem. So I'll try to talk about some epsilon expansions where epsilon is supposed to be some small parameters. So D is some kind of slightly larger than 2, maybe 2.001. And then naively, we can expand the solution in general D around 2 dimensions. And then the 0th order term is given by the 2D solutions. And then we have these first order terms, which is naively is linear in epsilon. So here we already make some assumptions. The first one is we already assume is a conformal field theories. Otherwise, it doesn't make sense to talk about capital G. And then we also assume that the leading correction to the CF data is linear in epsilon. For example, scaling dimension is given by the 2D value plus some correction linear in epsilon, also the OP coefficient. And then by using conformal bootstrap, we are trying to use the quotient equation to solve the CFT data. And again, this is some equation from the last week lecture note. I will call this combination capital F. And then, so the sum of these lambda square times F should be 0. And then we expand it to first order. At the 0th order is some 2D solutions, which should be some solution of the quotient equation, so it's just 0. And then at the leading order, we have a few terms. This is from the correction of the OP coefficient, and this is from the correction of the scaling dimensions. And then this is from the correction due to the external dimensions from this and this. And then the last term is due to the fact that conformal block depends on D. So it's a function of the space of the dimension of the D, and we need to take the derivative with respect to D, which also contribute to the linear order.
Can we stop about this? So what are the deltas and dels that you include in this equation so far?
Delta, they are the first order correction to the 2D data.
Yeah, but which 2D data do you take as an input?
So these are so this is from the 2D excess solutions. We know what the intermediate state. So in principle, all
but for example, I'm not sure. So the intermediate states in this case are going to be you have to take well, since you're considering sigma, there's going to be identity and epsilon. So you have to consider the descendants of identity and epsilon, decompose them into quasi-primaries. So you have to study the spectrum of quasi-primaries.
Right. So I discuss here, which is a bit later. So I can discuss now.
Yeah.
So the fusion rule is the product of the sigma. Sigma gives you identity and then the energy operator. And then we have this whole threshold multiplet and the other threshold multiplet.
Yeah.
And then if we decompose into the quasi-primary, they're given by different twists. So the first part is given by twist 4n with various even spin. And then the second part gives you the twist 4n plus 1, also with various kinds of spin. So these are the spectrum of the 2D solution. So we are trying to consider the correction. So this will be plus some epsilon times some unknown parameters.
But what do you do in the case there are several quasi-primaries which have the same dimension and spin? How do you have to, strictly speaking, like enumerate all of them and see what they are? Has it been done?
So to solve the mixing problem is difficult. So here we just talk about average. So in some sense, we don't need to worry about, we just talk about the overall behavior of around the same. To just talk about the average of the same degenerate, the several degenerate operator.
So you are assuming that to leading order and epsilon, you can basically take all primaries, quasi-primaries, which in 2D have the same dimension and spin, and you are assuming that when you go to 2 plus epsilon, you don't need to you can treat them as a single operator, basically.
Yeah.
Okay.
So in principle, we need to talk about, maybe I can go back here. So in principle, this degenerate operator can have different delta I1, but then in the end, we just take the sum. So it's just the average behavior will enter the equations. So,
well,
so maybe average times the OP coefficient square.
Okay, but suppose that there is among them a certain operator which has. Okay, I agree. It's not obvious to me that it works for the OP coefficients. Does it work for the OP coefficients without this trick? Can we go to look at the equation on the next slide? I mean,
and the OP coefficient squared in epsilon, not just the OP coefficient.
Yeah, so in principle, we to sum over all the degenerate case. So this I could also label the degenerate spectrum. But in the end, we just in the end we can consider some kind of average correction to the OP coefficient.
I think toward epsilon, everything you do is fine, but for the OP coefficients, you need, when you want to interpret it in the case with mixing, the interpretation of these quantities are a little bit complicated, but you don't throw in any problems by pretending the operators are non-degenerate.
But what I'm worried about is that what if there is some quasi-primary which in the Ising model has a 0 OP coefficient? Would this be a problem for this approach? Like, what would you have to do then?
So this is about this comment. So if they are 0, then they will not enter at this order, because we assume that the leading correction is linear in epsilon. So the square is second order. So you appear in the next order.
But might you expect square roots in that situation of epsilon?
Yeah, I will talk about this later. So here we just assume the very naive scenario. Everything is just linear.
Okay, it sounds.
That's the problem. This is, in fact, it turns out maybe not a good assumptions. So this is from the around 4 dimension. We know this is what we do usually, just a linear the leading correction, the linear epsilon. But here it seems that this is not correct in the end. So about the degenerate, in the end, this is not important for the analysis, because maybe you just sum over all the degenerate cases, then just more parameters. In the end, it just gives you some number here. Also this case. Yeah, I would also means the label of all the degenerate states, not necessarily with different delta and L. But in the end, this is not important. Please wait a moment. So this is an equation we try to solve to the linear order in epsilon. And then what I want to use is the so-called Lightcone bootstrap. The idea is to expand the quotient equation around the Lightcone. And here I will use the expansion in small UMV. And then the solution of the quotient equation should be symmetric in UMV after multiplied by this part. And then this means that the coefficient here should be some kind of symmetric. CMN equals to CNM. And then the exponent here it has some meaning in terms of the twist divided by 2, where twist is the difference between the scaling dimension and spin. And for example, we can see this example of the 2D solutions. After multiplied by this v to the 1 of 8, then this is a manifest symmetric in UMV. We can also expand this. And then one of the very crucial point I want to emphasize is that naively, we will guess that the spectrum of twist is given by all the integer numbers. For example, here we could have all the half integers. So the twist is naively is from 0, 1, 2, 3, 4, 5. But in the end, for the 2D spectrum of the intermediate state is more sparse than we naively see from this kind of expansion, from the tau here. So the spacing of the twist from the same Fiat multiply is given by 4 instead of 2. So for example, in the case of general free theories, it's given by 2, but here is 4. So in some sense, this is the main problem about how to deform this spectrum into larger than 2 dimensions.
But how do you see that? How is this consistent, the two equations? So you're saying, so suppose that I take the second equation and I just expand it in U and V at small U and V, and then I see what I get. Do I get indeed by just formally expanding it? Do I see that the spectrum of twists is degenerate because of some, or no?
So from here, we cannot see the degeneracy. So this is, we need to use the decompose the Virasoro character into the global case. So this degenerate is we cannot see from this solution of the quotient equations.
It just seems to me that the two equations are inconsistent, because if I take the second equation, I decompose, I just expand it, I will get, for example, the term linear in U, right?
Right,
and if
right.
I look at linear in U, then according to the first equation, there has to be some operator which has twist.
Right.
Twist
So here
Q,
we
but
also
instead
include the
twist is
descendant. So here is not just the primary,
Ah,
including the
here
twist
it's-
of descendant.
Okay,
So,
okay.
so that's why all the terms naively we expect all the twists could happen. But also naively we organize in terms of the whole multiplet. Naively this should be 2n instead of 4n.
Okay, I see.
So this is the main problem. If we cannot follow the more technical discussion later. So this is some basic dictionary for the Lightcone bootstrap. So in this double Lightcone expansion, we have some power law in U. This is a bit weird because if you look at single conformal block and expand it around V equals to 0, usually you only see the integer power and then maybe some single log. In order to have this power law, we need to sum over the whole large spin tower. And then the asymptotic behavior of the OP coefficient, the exponent P here is related to the P here. So a finite sum of the conformal block cannot give you a power law singularity. This require a whole trajectories with certain asymptotic behavior. And for example, in the case of 3 dimension, the vacuum contribution tells us that there should be a term looks like this. This can also be seen from this expression because the identity gives you 1 and then multiplied by v to the delta with a term which is v to the delta. And then by this symmetry in U and V, we have a term should be U to the delta sigma, and then divided by this. That's why we have this term. And then according to this dictionary, it means that we have some kind of a mean field theory, a large spin given by double twist, and then with certain asymptotic behavior for the OP coefficient. So this is the case for the 3 dimensions because we have the twist gap, and this is the leading behavior. And then the subleading one, for example, could be the stress tensor with the lowest twist. But the case of 2 dimensions is very different because we don't have a twist gap. From the vacuum, we also multiply. We have a lot of states, quasi-primary state with twist 0, for example, identity, stress tensor, and stress tensor square. And then it means that on the left-hand side, we do sum over all these low twist states. And then this gives you some kind of self-zero equation if we try to solve the quotient equations. So this would be more difficult than the case with the twist gap. Any questions at the moment?
So you basically propose to solve, you will solve everything by expanding in this limit of small u and v, and you're trying to figure out what happens.
Right.
Okay.
So now I will combine these 2 expansions. So before the linear order expansion in epsilon gives you this equation, and then we try to solve this together with the Lightcone expansions. So the first line is, roughly speaking, is some of the 2D blocks. So we have some parameters here, which is the OP coefficient, and then this is the scaling dimension corrections. And then second line is, roughly speaking, fixed by the 2D data. So up to this parameter related to the change of the external dimension. And this is due to the change of the D dependence of the Coulomb block. So we want to solve this equation using the Lightcone expansions. And the reason I talk about this dictionary is that in order to have this expand around V equals to 0, we need to sum over the twist accumulation point. And that's why in the end, what are the parameters here is not so crucial for this expansion, because in the end we do sum over all these states in the same trajectory, and then expand it around small v. So here I change it into the small z and small 1 over z bar. So in the end, this part will become this part. This is because the 2D block takes some factorized form. So k times k with delta plus L and delta minus L. And the other is like stranger in ZZ bar. And k is given by this 1D block, some XL2R block. And then without knowing these precise parameters here, we know that in the end, if we want to solve the equation near the 1 over in the small 1 over z bar expansion, this should give you some power law with certain power similar to the 2D solutions. So here, what we are constraining is the asymptotic behavior at large spin instead of the low spin individual data. And then because we are taking the derivative with tau with respect to delta, and this also gives some derivative with respect to the twist tau here, and this will give you some log. So in the end, this small f function also depends on contain some single log in 1 over z bar. So in the end, this f1, f2 is some power law, and potentially also with some log insertions to first order. So in the end, the first line becomes this.
But I'm not sure. Do you know these functions f explicitly, or do you just know what kind of form they should have? Because these functions f involve the sum of these coefficients that you don't know.
Yeah, we don't know, but we know what kind of power they should have.
Hmm.
And so this is similar to this expansion we just expanded, and then we know this this roughly speaking is 1 over z bar. So this should be 1/2 minus 1 over 8, and then maybe plus 1. So we know what kind of power we need in order to solve the equation near the small u and small v. So that's why I said this kind of degenerate issue is not very crucial, because in the end we are talking about the average behavior asymptotically at large spin. So what we are constraining is the large spin asymptotic coefficient. And then we have the other part, because we need to subtract the t-channel sum. And then we need to compute also the second line. This is easy, but then this is more difficult, because the conformal block is simple in 2 dimensions, but it's more complicated if we go to general dimensions. Even go to a little bit higher than d equals to 2. And so I only describe the steps I do here because it's more technical. So we can first use the 2D solution to derive what the large spin asymptotic behavior of the 2D OP coefficient. And then we use the general D conformal block. And this can tell us the corresponding leading term of the some result based on the 2D OP data. Sorry. And then we take the D derivatives and then set D to 2. This will give this, we can compute at least order by order in small z and 1 minus z bar. And then another way is to use some large spin behavior of the conformal block. So for example, this will give you, if we require that the leading power is given by P, then we know the subleading term is P plus 1, and then we have certain multiplied by some 1D block. So in this way, we can compute what the explicit series of these more complicated part based on the 2D solutions. And then we can try to solve the equation. But in the end, there's no solution if we want to try to solve this perturbative series beyond the first order in z and 1 minus z bar. So any question? Because this might be a bit technical, so I didn't show too much details. So what I do is try to solve these equations, and the first line is rephrased into this way, and then second line can be computed at least order by order, and then I just try to solve the equation, and then for arbitrary coefficient in these functions, there's no solutions.
Yeah, actually, I didn't understand. Okay, so you said once yeah, let me try to summarize. I'm not sure I understood. So you're saying we start with this equation in terms of OP coefficients. Then you said that if you want to go to small u and v, okay, you give some arguments that we can rewrite this equation in terms of some functions, which then you are trying to solve. But yeah, which equation do you finally solving? Like, okay, can you write an equation that you finally solving?
So the equation we are trying to solving is the coefficient of this small f1, small f2.
Equals to what?
So this will be equal to the second line.
But you don't know the second line.
This can be computed explicitly. So this I describe how to compute it. Okay. Just there's some explicit we can compute it order by order in small z and 1 minus z bar. So this is a technical part. I understand this might be not very familiar if we didn't work on this.
Yeah, but then in the end, what do you get? Like, so you get this, you compute this, but there's also.
So in the end, we can expand this equation around small z and small 1 minus z bar. So this is something we know up to these 3 parameters. And then the first line is given by some 3 parameters in the small f1, small f2. So the power is fixed, just the coefficient in this function is 3. And the problem is that I try to mention is that the tree spectrum is very sparse. The spacing is 4 instead of 2, and that's a problem why we cannot have the solutions.
So the second line is an expansion in z bar, z minus z bar, and it only has one free parameter, this delta sigma 1.
Right, only one free parameter.
Okay.
Everything is fixed. Just
And
it's more difficult to
the
compute.
first line, I don't see what is the freedom in the first line. Once you wrote it in these terms of these functions f and f1 and f2, what is the freedom?
So the f1, f2 is not fixed.
Yeah, what can you write what they are? I mean, what is they are assuming about them?
Oh, okay. So let me try to do it.
Blackboard's fine, should be fine if you can write on Blackboard.
So before we have the this solution is can you see it?
Yeah, you can see it.
Yeah. So this tells us that, roughly speaking, the power of the 1 over z bar should be 1/2 minus 1 of h plus n. Okay.
There is some reflection from the light. You shouldn't write where the light reflects. Oh yeah, yeah. We can see it. Okay.
Do you have if you have a whiteboard on your laptop, it will work perfectly.
Yeah, but I don't know how to share the screen, man. Yeah, I need some test to do it. But if this works, then I just continue to do it.
Okay, that's fine. But now I would be happy to see some equation for what is the assumption of the f1 and f2. Can you write like f1 equals something so that I see where the freedom is?
Okay. So f1 or 2, I call it k. So in order to solve this equation, we know what kind of power we need to have. So it means that it should be a 0. So these are all kinds of all the integer power, and then we also have the log. Just something very similar.
But why are you assuming that the powers are the same?
Because in the end, we want to solve the equation. Otherwise, if it's different power, then it will not be consistent with this kind of. Oh, sorry, you cannot see it now. It will not be consistent with this kind of.
No, but you see, it's not logical. Because these functions f are defined by the left-hand side of the equation. It's the sum over this p coefficient squared, variations of p coefficient squared, and so on.
Right.
So why don't you write me some properties of these functions f which follow just from the left-hand side of these equations? And then we will later on see what follows from the right-hand side of this equation and see what extra properties need to be satisfied. But right now, it seems like you are putting together everything. It's not clear to me where this falls. It falls from the right-hand side or from the left-hand side of the equation. You see my problem?
Yeah, I understand. Yes. So the problem is that so this again is related to why I talk about this part. So in the end, we want to go to small u, some small v. What is important is the asymptotic behavior of the OP coefficient at large spin. So so in the end, what we need to do is we sum the whole contribution on the left-hand side and expand it in small v. But then this is since we don't know what is the lambda 1 and this delta 1. It's difficult. We cannot do it. So what's the logic here is that we directly constrain what kind of large spin asymptotic behavior of the OP coefficient should look like.
Well, I'm not sure. Maybe some other people can help to explain. Jochen, do you understand what's going on? Can you summarize? Because I'm lost.
So, in my impression, the little f's, they're defined by the left-hand side in the expression. But in the sum in the left-hand side, you have now divided all the operators into twist families. So instead of summing over all the operators, you now only sum over the possible twists in the theory.
Okay.
Then, from the assumption that all operators, there are no new operators, essentially, is one of the assumptions that later in the talk is going to be incorrect, if I understand where you're heading when they are. But since you assume that there are no new operators here, the sum of the twists in the left-hand side is the same as the values for tau in the left-hand side is the same as those you have in the free theory. So you're already getting some structure of how you expect the left-hand side to look like. And now you want to match this with the right-hand side. And you're solving this in the limit of small z and small 1 minus z bar.
Okay, but my problem is this. Let's just look at one term of this function f of 1 minus z bar, which corresponds to a sum over a twist family. So, given that this function f of 1 minus z bar corresponds to a sum over some twist family, what do we know about this function? Because it's a sum over a twist family, but it's a sum with some unknown coefficients, which we don't know. Right?
Yeah.
So given our partial information about this function of twist family, what do we know about it? Just from the left-hand side.
Yeah, I understand. Yeah, I understand the question. So we don't anything. We don't know what is these things before we do the sum. So in principle, this f1, f2 can be some arbitrary function of 1 over z if expanded around z bar near 1. So in principle, this could be arbitrary function because we have arbitrary parameters here. And I skip one step is that, and then we need to know what kind of behavior of this small f should have in order to solve the quotient equations. For example, I mentioned this example is because that this v cannot have arbitrary power here. Otherwise, we cannot solve the quotient equations. It should match the spectrum, the tau here. So in principle, it's an arbitrary function. But then if we want to solve the quotient equation, we know what kind of power it has. And this power just comes from the last spin asymptotic behavior. So in this way, we know what kind of f1, f2 could have up to the coefficient in front of all kinds of power.
Actually, if you go to the next slide.
Yes.
Oh, the one after.
This
So
one?
actually I would expect next to F1R there to be a Z power, Z to the tau over 2 or something.
You mean which one?
Yeah, well, in this, again, actually in both of these, so maybe outside the bracket there, I would expect it to be a Z to the tau.
Yeah, it's inside this K.
Oh, it's inside that K. I see.
Sorry,
Yeah,
yeah.
great.
So there are two parts. So I use the exchange part. So one depends on Z, the other depends on Z bar. But the second term is this becomes Z bar, this becomes Z, and this is the tau. So what we do is just sum over this part, which is to be the function of Z bar, and then expand it around Z bar equals to 1. In principle, because this arbitrary, this F1, F2 is also arbitrary, but just in order to solve the quotient equation, we know what kind of power it has. And then, so this is why I talk about this, I emphasize this many times. This cannot be arbitrary. Otherwise, we just cannot match the other side. And then, so the only 3 parameters in this F1, F2 is just the coefficient of this different power.
Okay.
And what we do is just to try to solve, put this into here, replace this with this. And then the second line is known, just we can compute it order by order. And then it turns out there's no solutions.
Yeah, and maybe Slava, I think you should perhaps think about the fact that there are no solutions. That shouldn't be a surprise to us. Like the large spin expansion and the D goes to 2 expansion shouldn't really commute.
I see.
Like maybe each operator will be continuously deformable from 2D to higher D, but it's not like a uniform deformation. The higher you go in spin, the quicker the operators must move up from their Virasoro multiplet to the double twist value, exactly as Andrea showed us on Friday.
Yeah. I see.
But maybe we want to hear the next part of the talk.
So basically, the idea would be that it was not such a great.
Sorry.
It was not such a great idea to expand around this Lightcone limit and hope that things would be nice. But for example, if we were expanding around some middle point of the causal diamond, then we would expect that things would behave nicely in the epsilon expansion. But there, of course, it's much harder to control things.
Sorry, there is maybe a question by Andrea Capelli.
Yeah,
who
yeah.
has raised the hand.
I mean, assuming that the calculation that has been done is correct, I think there is the fact that there are no solutions is due to the fact that you didn't allow some channels which are 0 in D equal to 2, meaning that the Ising model above 2 dimensions is not a minimal model. So, and once you introduce operators which are not in the CATS table, then they become, as we saw, leading in epsilon, because they will count like epsilon square in this expansion, okay? So if you replace the parameter of expansion from epsilon to say delta square, they will be leading in order delta. And so I think that's the main problem. I think I remember an argument, I'm not able to repeat by Rastelli, that's saying that, for example, if you want to satisfy the stress tensor conservation, when you have an extra dimension, then you have to introduce an extra field, okay? Because for example, let's take 3 dimension and let's take that the derivative involves 2 components in originally, and then there is a 3rd component, okay? So the extra term is an extra field that doesn't exist in the Ising model. And so I think you can make an argument that you have to enlarge the space of fields, and at that point that part is dominating. End of the comment.
Yeah, I agree that assuming the spectrum is the same is kind of problematic. Later I will talk about something related to this. Maybe I will try to come back to this point. Yeah, okay. So one of the problem here is whether this kind of expansion around the Lightcone and this epsilon expansion, whether they are kind of commute or not. But I guess in the case of 4 minus epsilon dimensions, this we can just exchange without any problem, because in principle, at each order, we have some exact solution to just obey uniformly. It doesn't matter whether we take so if we have one solution, then this should just be a solution to the crossing, and we can evaluate this near any point. We can do the Lightcone expansion, and I don't think there's any issue about commuting, because we already talked about this part, no?
Yeah, but when you expand around the 4 dimension, you expand around the field theory, which has all the possible fields in the expansion as you like. If you expand around the Ising model, you expand around the minimal model. And so you're using a
right,
which is smaller. So my conclusion of your result, but please keep going in your talk, is that you cannot start from you have to enlarge from the minimal to non-minimal theory in 2 dimensions to see this expansion. But please keep going.
Right.
No, but Andrea, why are you saying this? Because I don't think you presented in your talk any evidence that the number of quasi-primary fields has to be enlarged in 2 plus epsilon dimensions compared to 2 dimensions. It might still be the case that there's the number of states in the theory is at least in this correlator is the same. I don't think so. Some other assumptions may break down, like Lightcone, or the fact that everything there is analytically an epsilon without square roots. But the fact that the number of the extra fields are needed, I don't think it was obvious from. I mean, I asked you several times, can you prove that there are extra fields? And you said no, my precision is not sufficient. I pressed you on this.
Yeah, in fact, I thought to your remark is that the point is that the limit d equal to 2 is a limit in function space. So you have to say how you do the limit. It's not automatic. So how you weight the different, how you test the space with some distribution and in spin, and the limit is different according how you define it. Okay. So my results do not bring any information about this discussion. So you can say the space is infinite. In fact, for any d bigger than 2, the number of states involved is infinite. But then doesn't make sense. To make sense of this limit, you have to define the limit as a certain limiting function space. So.
No, but but I don't want to count
the limit. You get different result. Okay.
No, but I don't just want to count the number of states. Of course, it's infinite for any d. But my question was, let's, for example, in d equal 2, we know that sigma exchanges epsilon. There is just a single operator of dimension 1, which is being exchanged. Now let's look at d equal 2 plus epsilon. Will there be a single operator of dimension 1, or will there be perhaps, let's say, close to 1, or will there be perhaps 2 quasi-primary operators close to 1? Scalars. That's a well-defined question. And we believe that in d equal 2 plus epsilon, there will still be one scalar quasi-primary operator of dimension close to 1. We believe so. Now let's repeat the same question for other quasi-primaries, higher quasi-primaries. Let's look at the next quasi-primary in the sigma PE, which is in dimension 2, it's TT bar, which has a scalar quasi-primary, which has dimension 4. Let's see, in 2+ϵ, is there a single quasi-primary, scalar quasi-primary with dimension close to 4, or is there several quasi-primaries?
It depends on you. You choose.
No, it doesn't depend on me. There's going to be a unique solution if you look at the, if you extremize things and so on.
No,
It doesn't depend on me.
Yes. Well, okay.
It doesn't depend on me. How can it be depend on me? Let's extremize. Let's do the central charge extremization like you did. And let's extract the spectrum with infinite precision. Does the spectrum contain 2 quasi-primaries or 1? We should be able to figure this out.
Yes, that's true. But that's true. That's true. But how to implement in this discussion of today's seminar?
In today's seminar, it's being implemented a little bit. Of course, now Van Lang assumes that there's going to be a single quasi-primary, but in addition, he assumes that the dimension of this quasi-primary is going to vary linearly in epsilon. That's an extra assumption, which may or may not be true.
Okay, you do this assumption and you see what are the consequences.
Yeah,
If
okay.
it doesn't work, you have to change your assumption. That's the way I told you.
Okay, great. Yeah, let's see what Van Lang else has to show us. Sorry, Van Lang, we monopolized, but now you can go ahead, please.
Yeah, well, I understand. Yeah, this point is quite crucial. How I showed there's no solutions under my assumptions. So if there's no solution, I mean, if my argument or my computation is correct or valid, that means that at least one of my assumptions is not correct. So we need to relax the assumptions. The first one is whether in above 2 dimension, whether you still have a conformal invariance, or we just maybe have scalar invariance. But I guess most probably it's still conformal invariant because we know in 2D, 3D, and slightly below 4D, it is conformal invariant, very strong evidence from numerical and from analytic studies. And then I guess the more possible problem is about the assumption about the CFD data, how they are corrected in epsilon. So I assume that they are linear in epsilon, but in principle, they could be more singular in order to solve the problem. So here the power should be some more than 1. And I mentioned the problem about this, why we don't have solution is that this part is in some sense is more difficult because it's not factorized. Because in this equation, in the end, we want to decompose this into some kind of factorized building block. But already, if we go to larger than 2 dimension, this kind of this D dependence will give you some kind of non-factorized properties. And that's a problem of the solution, why we cannot find solutions. And if you assume that the leading correction could be more singular, then in order to match this difficult part, it's better to assume that this exponent is 1 over k, where k is equal to 2, 3, 4, 5. So in the end, in some order, this will give you some contribution to epsilon to the first, to the 1. And so the simplest possibility is that the leading correction to the CFD data is not linear, but instead is epsilon to the 1/2. And again, in order to solve this quasi equation near the Lightcone, we need to have an infinite number of states, some infinite high spin towers to have deformation given by this form in order to create the correct Lightcone singularity so that we can solve the quasi equation near the Lightcone. And then there are few possibilities. For example, we can require that the state already appear in 2D to be corrected by epsilon to the 1/2. And then the other possibility is that maybe there's some state which is the OP coefficient is 0 in 2 dimensions, but then it is corrected by epsilon to the 1/2. In this way, to the linear order, this could also appear because the square of lambda is linear in epsilon. And I want to emphasize that the problem before is that the spacing of the twist is too large. It's given by 4 instead of given by 2. Therefore, if we introduce some new state, new trajectories, where the twist is taking these values, in the end, the spacing of the twist is much smaller, and it's much easier to have solutions. So this is some discussion I want to emphasize about. For me, the main problem is about in 2 dimensions, the spacing of the twist spectrum is too large. This is very special for 2 dimensions. For example, you can see there's some special property of the conformal block in 2D is that it is invariant under this shadow transform. So in 2D, just 0, so L becomes minus L. This gives you the other terms. So the conformal block is invariant under this transform. It means that the OP data is also invariant under this transformation. And then it means that the twist spacing is related to the spacing of the conformal spin. And then for the case of conformal spin, the spacing is given by 4 because here is given by 2L. And then for here we consider the correlator of the identical operators. And therefore is 2 times 2 is given by 4. And that's why here in the case of 2D solution of these identical operators, the spacing is given by 4, which is very special. This can also be derived from decomposing the Virchow block into the Goro block. We can see that the twist is given by this 4n and 4n plus 1. But then when I preparing this slide, I noticed one problem is that although in this OP spectrum we have this large spacing, does the 2D Ising model also have this large spacing in the full spectrum? So here I use some formula from this paper, from this work. So the main idea is to decompose the Virchow character into the global one, and then we can count the the multiplicity of the global, the quasi primary. So we can see that there's some state that do not appear in the OPE of the sigma. For example, you can see here this one has the twist 15, which is different from this or this, and also this is given by a full trajectory with spin 2, spin 4, with twist 15. So it means that although the theory contains some state with large twist, but they do not appear in the OPE of the sigma. And that's why I think the problem is that for some reason, if you go to 2+ϵ dimensions, this large spacing of the twist spectrum should be reduced to 2 instead of given by 4. And in this way, it's very easy to have solutions. And here, what I talk about, I want to discuss about the work by Golden and Polish, where they studied numerical bootstrap in D between 1 dimension and 4 dimension in 2 dimensions. And we know that above 2D, we have a very nice single kink phenomenon. However, if you go to below 2 dimensions, it turns out that instead of 1 kink, we can see there are 2 kink. This one and this one. If we go to lower dimension, then the distance of the 2 kink becomes larger. This can be seen more clearly if you look at the spectrum, where the rearrangement takes place at different points. So here is given by 0.122, and this is given by 0.119 or 120. So instead of a single kink, we have two kinks. And so I guess there's one figure from a reference mentioned in Slack. So maybe the reason is that instead of, so if we go to lower than 2 dimensions, the true theory is outside of the bound. And the reason that we cannot see because there's some low-lying and non-unitary state, and we need to cut out this space. And in the end, we cannot see the true theory. And that's why we can see two kinks instead of one kink. And this is consistent with the scenario that there's some kind of new state where the OP coefficient is linear, is given by sigma to the 1/2. If we go to lower than 2 dimensions, this becomes kind of imaginary. So the square root of lambda is negative. And therefore, we have some kind of non-unitary setter. And that's why we cannot really see the real theory. But if we go to lower than 2 dimensions, and it's outside of the bound, and we see two kinks. So what I want to say here, if we introduce more stage, not just the one we see in the 2D solutions, also if we also introduce the twist given by 4m plus 2 plus 3, then it's very easy to find solutions after we reducing the spacing of the twist spectrum. And then in fact, there are too much solutions. And this is expected because we just use one of the Gaussian equations. We also need to use the SU Gaussian, but then this we cannot study using the Lightcone expansions. And then another problem is that if we can solve the Gaussian, we still don't know whether this is the Ising solutions. And in 2 dimensions, we know it is characterized by some kind of decoupling. For example, if you follow the interpolating solutions, some similar to the extremal function, extremal spectrum, then we know that some decoupling happened at the kink, where the twist 1 spin 2 operator decoupled, also the full twist 5 trajectory decoupled. And then the question is that whether this kind of decoupling persists if we go to a bit higher dimensions. And the result from this work shows that it seems that this subleading spin 2 decoupling persists, but then already the scalar of the twist 5 trajectory just partly decoupled. It decoupled below roughly below d equals to 2.2, but if you go to higher dimension, it seems that they do not decoupled. So there's some question about, yes.
Can I ask a question? What do you mean by decoupled? Do you mean the operator still exists in the spectrum, but it has a 0 OP coefficient in the sigma 4-point function? Or does the operator cease to be part of the theory at all?
I will become the null state in the case of 2D Ising model. Is
but
just have zero norm.
Does it exist in other 2-dimensional models, or does it exist in the Ising model in, say, 2.1D?
You mean in larger than two dimensions? And then I don't know. I'm not sure. So what we see,
decouples, it means that you're comparing with the other 2-dimensional theories, like the minimal models.
Yeah. So this is about the 2 dimension is more clear. We know the exact solution of the kind of the boundary, the interpreting solution for different minimal models. But just we can see that this is related to the null state condition of the 2D Ising model. You mean whether this were about the case of the larger than 2 dimension, then this is a more difficult question. Then I'm not sure about the answer.
Okay.
So just from the numeric, it seems that this spin 2 decoupling persists. But this is characterized why we have the kink, because we want to go beyond the kink, then this spin 2, but not necessarily twist 1, it could be, this will be changed. But then the OP coefficient square becomes negative. That's why we have a kink. We cannot go beyond that point. But then whether we have more decoupling is a more difficult questions because they are not the low lying operators. It's not very easy to see them numerically. I guess is less stable. And in the end, there are also other. So I want to say there are also other consistent requirements. We find some kind of solutions. So, so to summarize, what I want to show is that if you assume that the 2D data is deformed linear in epsilon, there's no solution if we go to slightly above 2 dimensions. But then if we allow that to be deformed, for example, fractionally, by fractional power of epsilon, then it's possible to have solutions. And then maybe we can try to solve the OP coefficient by using some tentative spectrum. And then we can see whether this kind of solution is consistent. Then maybe we can extract the numerical value and then try to guess what are the analytic counterparts. And then again, maybe there's some point is not very easy to follow is that I emphasized many times is that in the 2D case, the spacing of the twist spectrum is 4, is kind of large. That's why we cannot find solutions. And this is some peculiar property of the 2D because the global block it will sum into the Virchow block. They are they are kind of correlated to each other. But then there's some special property that we cannot, I guess, cannot preserve if we go to larger than 2 dimensions. I guess there's one question. Yeah, please.
Yes, you can finish, but okay, let me ask you now. So on top of these issues, there is another well-known issue, no? That theories in fractional dimension, safety in fractional dimension are not unitary. Now, as a matter of fact, experimentally, at the Euclidean point z equals z variable 1/2, you see nice kinks, and it seems that this non-analyticity are small, numerically very small, and then nobody cares. Now, I don't know. Do you think that in the Lightcone limit they might be large, or even if you want to analytically solve, they might give you? See, you don't find the solution because we are not taking care of this non-unitarity that might change your function. We are using unitarity indirectly by using the Lightcone bootstrap result. So, can you comment on that?
So in some sense, the Lightcone bootstrap is not very sensitive to unitarity. So unitarity is not very important in the Lightcone bootstrap because we are considering some kind of average behavior of the asymptotics instead of look at the individual operator whether one of them is negative or not. Just talk about the average behavior. And so it's not very easy to see non-unitarity.
Sorry, you inject the minimal twist typically of unitary theories. No, you don't assume that there might be some weird operator below some twist gap. No, so indirectly you are doing. You are
right, about the
assuming
spectrum.
unitary.
Yes, so I guess you are referring this part. So in the 3D case, typically the argument is based on the unitarity gives you some unitarity bound. Therefore, the lowest twist given by the vacuum, and then the other state has some gap is larger than the lowest one is maybe given by some constant current. And then because of this gap, we can map the leading behavior to some double twist trajectories. So the discussion in this talk is a bit different. We start from the 2D. 2D is very different because we don't have the gap. There are many quasi-primary where the twist is 0. So that's why if we try to solve this using some analytic bootstrap method to solve this problem is very different. Everything, this kind of 0 twist states all kind of entangle each other is not the same as this simple story here. So here I would say I didn't use unitarity very explicitly, even about the spectrum. Is it clear? Did that answer your question?
Yeah. I mean, if this large asymptotic average works also for non-positive OP, now during all that, I think it's fine, yes.
Yeah, I mean, it doesn't matter, just put a minus here, then we give a minus here.
So your problem with the twist would arise for any 2D minimal model, is that right?
So the twist, so I can say again?
I mean, you chose the case of the Ising model, which C equals 1/2, but if you chose some other minimal model with higher C, would the same problems arise?
I'm not sure, but naively, I will guess the similar problem because, again, for me, the crucial problem is about the twist spacing is too large. If we are talking about the identical correlations, it's given by 4 instead of given by 2.
I was thinking if you chose C very close to 1, which is
Yes.
close to a free scalar field, I mean, and then you know what the states are for a free scalar field, what would the situation be then?
Oh, okay. Yeah. Okay, I need to think about it. So it's just given by free theories. Then I guess there should be no problem. It's just free theories. If we deform it to larger than 2 dimensions.
I was thinking of C very little bit less than 1, but still one of the minimal models.
There is also the nonlinear sigma model expansion. I mean, somehow probably it's an expansion around the free theory.
Yes.
So I was wondering how this relates to the standard 2+ϵ expansion and the nonlinear sigma model.
For me, I guess free theory, there should be no problem because I guess all the stage you see in the spectrum, if they are not forbidden by some symmetry, they are allowed to appear, which is different from the discussion here because naively there's some state that could be inside the OPE, but somehow they just have 0 OPE coefficient. And because of some constraint due to the philosophical symmetries. So answer is, I guess, for free theory, there should be no very serious problem for weakly coupled theory. So this is some special feature for the strongly coupled theories in 2 dimensions.
Okay, so I mean, the discussion has entered, let's say, in a continuous phase transition to the question time. So I think that we can, we still have some.
I think there is a question. I think there is a question from Mikola.
We still have some minutes. Then I mean, we can go on. We can go on.
Yes,
And
please.
Andrea also wants to ask a
Andrea,
question.
yes.
So Mikola, can you ask a question? No. Well, then Andrea.
I think with some little effort, one can make an argument that you do need extra fields. For example, consider the fact that the conformal field theory in 2 dimensions is an integrable model. So there are infinite conserved currents, which are the powers of the stress tensor, normal order power of the stress tensor. Okay, so above 2 dimensions, you don't expect integrability. So you will need extra fields to obey conservation, to break this conservation. So
well, no, Andrea, it's actually the other way around. So this is called multiple recombination phenomenon. It happens also around 4D because in 4 dimensions, free scalar also has infinitely many conserved fields, currents. But then if you go to 4-ϵ, all these extra currents are no longer conserved. Only stress tensor is conserved. and the number of quasi-primaries is reduced because this conserved currents in 4D, they get combined with some extra primaries to form a single quasi-primary non-conserved in 4 minus epsilon d. So this effect reduces the number of quasi-primaries as you depart from 4D to 4 minus epsilon.
Yeah, but the point is that the starting point is free theory, which has all the states, while here the starting point is a minimal model which has far less states.
It has far less states. In fact, you can ask the following question, which is an interesting question. Does their two-dimensional CFT contain some quasi-primaries of the right dimension so that all Virasoro, extra Virasoro currents, which have to become not conserved in 2 minus epsilon, in 2 plus epsilon, they actually can eat. So it's a sort of Higgs phenomenon. They can eat. They have to eat someone in 2D to become non-conserved. And you can ask the question, does the two-dimensional contain all these fields to be eaten? If it did not contain those fields, it would be a big problem. But I think it does. I'm not sure. I think Leonardo Rastelli told me once that he did this check. I don't know. Maybe somebody else in the audience knows this.
Oh, yeah. So on its own, the 2D Ising model appears not to contain enough fields to recombine. And you can make it contain enough if you formally put the null states back in, but that might not be the correct procedure. It might be what Andrea is saying of actually adding new quasi-primaries.
Aha. Okay, so you have to add. So that's interesting. So is this published somewhere?
We couldn't get it to work beyond just this no-go observation.
Well, no-go observation is also interesting. So you're saying, but can you be a bit more specific? So which field, for which first field this happens?
I don't remember, but it was pretty early. It might already be the spin 4 current.
But so you look at the spin 4 current, and you're saying there's no like spin 5 guy, spin 3 guy, which it could eat to become non-conserved.
Yeah, spin 3 dimension 5.
Okay, well that's a pretty. So you have to add this guy, but then once you add it and you go to 2 plus epsilon, it's eaten. So the number of quasi-primaries, if you just have to eat that guy, which immediately gets eaten, then the number of quasi-primaries is still the same. But it is an indication that something weird is going on indeed.
I have a question. What is the story of the fermion above 2D? Because like we know the 3D Ising model does not have a local fermionic operator, and we know in 2D that it does. So like, how can we even attempt to have some kind of epsilon expansion if the spectrum is just completely different because this fermionic operator appears in one case and doesn't appear in the other case?
Fermionic operator appears in 2D. In which case this appears?
I don't know. My short answer is
I mean, I understand the correlator you're looking at. This question isn't relevant because you're looking at a correlator of scalars. But I'm just saying, if you have the general question of how is it you go from an exactly solved theory in 2D to a theory we're trying to understand in 3D, there just seems to be this discrete change, which is that one has a fermionic operator, one doesn't have a fermionic operator.
No, I'm sorry. Ising model doesn't have a fermionic operator. What are you talking about?
Wait, sorry, with the 2D Ising model?
It does not have a fermionic operator.
Wait, what do you mean? Hold on. Isn't that one of the Virasoro primaries?
It's not. It's not. It only has 3 Virasoro primaries, I, or unity, sigma, and epsilon. This fermionic operator that you're talking about, it's not a Virasoro primary. It's some like, it doesn't have local correlation functions, for example, with sigma. So you cannot add it to the theory as a local field. It's not a field of the theory. It's just, if you want to think in terms of Ising model, you have to like quotient by some stuff. It's not, yeah.
So, sorry, but like, but I mean, what's the barrier? I mean, I thought in the original paper by Schenker and Fradkin, they say there's a spin half dimension half operator, but.
No, people like to talk about this fermionic operator, and they like to be vague about, is it there in the theory or is it not in the theory? But if you want to think rigorously, the fermionic operator is not a part of the theory. It appears in some like intermediate steps of solving the theory, but once you solve the theory, it's like intermediate steps, but in the final step, you get rid of it.
Okay, all right, okay, sure. Okay, so I guess that's not an issue then. I also had a question for the audience in general. So like there's this old story by Polyakov where he was trying to say that like the same way you can solve the 2D Ising model by writing it as a free fermion, you could attempt to solve the 3D Ising model by writing it as like a fermionic string. And I understand that like, I guess on the level of the lattice, you could try to construct something like that, but no one was ever able to find a continuum limit. So have people ever tried to do this in 2+ϵ, in which case I don't know, maybe it would be more feasible? Because you know, then it would be like very close to like some kind of like local model instead of being something which is very non-local.
Yeah, I'm not sure. It's a lattice construction. It has not been, it's hard to do it in 2+ϵ because it's not a continuum construction. So
yeah, I understand. I understand that usually they construct that on the lattice. I'm just saying that like, if you're trying to guess, like, I don't know what the right continuum description would be, maybe that'd be easier doing it in 2+ϵ than directly in 3.
Perhaps, yeah, but I don't think it has been done. In fact, it's kind of weird because there's people who did this fermionic string for the Ising model. They are they don't want to disavow this construction because they hope that perhaps one day it will work. But if you ask them to give talks about it, they refuse. So I organized a conference where I asked Dotsenko to give a talk about it, and he said, no, ask Polyakov, it was his idea. I don't want to have it to do with it. And I asked Polyakov, and he didn't want to give a talk either. So my interpretation is that they don't know how to proceed with this idea. So like, honestly, they should just say, no, it doesn't work, but they don't want to say this.
So I was doing a bit of Googling, and this past year, there was a paper by McGreevy and Iqbal on some update of this idea. I mean, obviously they haven't solved it, but but it does seem that people are still thinking about it.
Yeah, they tried to think, but it was the end result of that investigation. Okay, we had a talk about this in the Bootstrap seminar. It's recorded by McGreevy, but the end result of the investigation is that it doesn't work.
Oh, okay.
Yeah, so we didn't find anything new. But it's in the Polyakov's book. Yeah, you can look at it and you can try to see it.
I also had a question. There was a proposal, I think it was you, who said that you could expand around the different minimal models. So what would you expand towards? You expect there are different theories which you reach by expanding from that?
In this comment? Yep, so what I mean here is I see some obstruction of extending the 2D Ising naivety above 2 dimensions. I guess there's some similar obstruction if we do it naivety for other mini models. And it doesn't mean that it doesn't work, just we need to do it more carefully. Maybe some more exotic, for example, this fractional power of epsilon in order to make it work. And I don't know, so some of the mini model can have some 3D realization, but I guess not all of them corresponding to second order phase transition in 3 dimensions. And then there's some question about how they disappear in the middle between 2D and 3D, but whether this can be seen also analytically using these 2+ϵ dimension discussions. I think this is interesting, but I don't know whether this can be done, because already in the 2D case, for the Ising case, I see some difficulty. I guess the other case is more difficult. But numerically, I guess still one can try just vary the dimension to see whether can persist or not, or whether there's some can we combine. Maybe there's some talk this week about this problem.
So the only field theory I could see would be phi to the probably 2n, and the critical dimension would be somewhere between 2 and 4. I mean, the bigger n, the closer the critical dimension goes to 2. I don't know whether this has been exploited.
You mean some interplay between the large N expansion and then epsilon expansion around 2D?
If you take phi to the 2n, then you can do an epsilon expansion, but the critical dimension is between 2 and 4. I mean, given by power counting with a Gaussian free field.
Okay, yeah.
I mean, phi 6, for instance, is it's around 3 dimensions, and can be used, for instance, for tri-critical polymers and stuff like this, depending on them. Oh, and different end we were now talking.
Okay. So I guess if we choose other end, then the upper limit is some fractional dimension. It's not at the integer, right?
Yeah.
I don't know, 5 to the 10 or 5 to the 12, I don't know.
So these models wouldn't exist in 3 dimensions. It would exist in 2.001 or something like this. But I mean, for higher n, but not in 3 dimensions.
Yeah. I guess, yeah, it would be interesting to starting from long integer dimension, maybe do some maximum expansion around these cases.
Sorry, there is Nicola Spot that has raised the hand. Maybe he has a question.
Yes, I wanted to ask, maybe it would be reasonable to look at this problem in terms of the semi-infinite system, because there you must not consider the 4-point function. There you can treat the 2-point function, and this function depends only on one variable, not on the two, as you have now. And conformal blocks are known and relatively simple. And there are also two kinds of conformal expansions in blocks expansions: boundary block expansion and the OPE expansion. So what would you think about such possibility?
I guess, yeah, this kind of defect of boundary bootstrap, I guess the building block and the cross integration is easier because we have only one variables. Yeah, I think it would be interesting to try to deform this from 2D and try to see 2+ϵ dimension, whether this works. Yeah, indeed, it should be easier because only one variables.
Okay, maybe I have to, at least the people who are present here, I think that they have to go to eat.
Yeah, we should
So
thank them for this discussion.
Yeah, so we can, I don't know, we can close the discussion or you can continue on remote, I don't know what we do. We close it and we can pass on Slack. If
At least people in, we should close, we should continue on Slack and people can, yeah.
Can go to it.
Yeah.
So thanks a lot for this discussion, and so I will end the registration and the meeting. Thanks a lot.
Thank you.
Thanks a lot.